As I was saying at the end of the last video, just before the battery on my camera died, if we look at the cyclic alkanes and assume they're planar, and we go from the 3-membered ring cyclopropane to the 4-membered ring cyclobutane, 5-membered ring cyclopentane, to cyclohexane, cycloheptane, and cyclooctane, we gradually predict an increase of 2 kilocalories per mole as we add an additional carbon from 6 kilocalories per mole of eclipsing strain for the cyclopropane, 3 hydrogen over hydrogen eclipsing torsional strains on the top and 3 on the bottom of the molecule, to 8 to 10 to 12 to 14 to 16, because every time we add a CH2 group, we add 2 additional hydrogen-hydrogen eclipsings, one on the top face and one on the bottom face. But what we actually see in the ring strain is 27.6 kilocalories per mole ring strain, which is much larger than the predicted 6. 26.3, which is again larger than the predicted 8, and then a gradual decrease to a minimum of 0.1 or almost no strain at all for the cyclohexane ring, and then slightly increasing as we go into the larger rings. And I was saying that this proves 2 things. One, it proves that the 6-membered ring and the 7 and the 5-membered ring are not planar, because if they were planar, they should have 10, 12, and 14 kilocalories per mole strain, and they'd be respectively not 6.5, 0.1, and 6.4. And there's another source of strain that is not the eclipsing torsional strain that will need to be invoked to explain these really big differences between the actual ring strain and the ring strain predicted from hydrogen over hydrogen eclipsing interactions for a planar ring. The larger the ring, the more conformational flexibility there is, and the greater the ability it has to take on a non-planar structure to relieve some of its eclipsing strain. Cyclopropane, of course, has no flexibility at all. There's no rotation possible without carbon-carbon bonds, without breaking the other 2. And you see that the strain per CH2 group drops quite a bit when you go from the 3-membered to the 4-membered ring, and then drops precipitously when you go to the 5-membered ring, to almost, and then going back up a little bit as you go to the 8-membered ring. So we need to explain the origin of this large difference in the strain energy that we see in the ring strain for the small rings, and we need to figure out what the actual preferred conformation is for the larger rings that deviates from planarity that allows us to relieve the eclipsing strains. So in this video, I want to focus on the first question, which is, what is it about the structure of the 4 and 3-membered ring systems that cause such a large ring strain, 21.6 kilocalories per mole larger for the 3-membered ring, and almost 18 kilocalories, 18.3 kilocalories per mole larger for the 4-membered ring. And this has to do with the angles for the carbon-carbon bonds. So if you consider the bonding using a valence bond picture for cyclopropane, we know that those 3 carbons are going to take on the positions for an equilateral triangle, which is 60 degrees. And then we have our hydrogens. Above and below the plane. But we also know that the hybridization on the carbon atoms, because there are 4 electron groups, is sp3, tetrahedral. Well, the angles, the intra-orbital angles for an sp3 hybrid orbital are at 109.5 degrees from each other. Right? So the preferred angle for an sp3 hybrid orbital with another sp3 hybrid orbital is 109.5 degrees, but the bond angle is constrained to be 60 degrees. And when you go to the 4-membered ring, if it's planar, the bond angle is 90 degrees. assume the carbons are sp3 hybridized, so the interorbital angle is the same 109.5 degrees. That's a big difference. And the strain that results is called bond angle strain. It's a result of the bond angles being forced to be much smaller than the orbital angles. And the result of that, if you think of this carbon-carbon bond as being formed from the overlap of two sp3 hybrid orbitals, which is what we would normally do in a linear system, we would have our sp3 hybrid orbitals at 109.5 degrees, and we would form a carbon-carbon bond by overlapping one sp3 hybrid orbital with another sp3 hybrid orbital, or in the case of the carbon-hydrogen bond, an sp3 hybrid orbital on carbon with a 1s orbital on hydrogen. In a linear system, there would be no problem with having these electrons directly between the carbon-carbon nuclei and having a 109.5 degree bond angle. And then we also have the two hydrogens that are not in the plane of the board on each carbon. So if we think about where the orbitals are, the orbitals that are forming this CC bond are out here, not between the nuclei. So that the angle between the orbitals can be the 109.5 degrees that's required for an sp3 hybrid orbital. But that places the electron density outside the bond axis. And we know that the other type of orbital that places electron density outside the bond axis is a pi orbital. So it's perhaps not surprising that the carbon-carbon bonds in cyclopropane are significantly weaker than an ordinary carbon-carbon sigma bond, because the electrons are not between the nuclei where they need to be if they're going to prevent nuclear repulsion. If the nuclei can see each other, the nuclei can repel each other. And that's what we see in fluorine, F2. And the reason why fluorine gas has a bond energy significantly less than chlorine, even though the atoms are smaller, right? Fluorine bond has about the same bond association energy, about 38 kilocalories per mole, as the iodine-iodine bond, despite the fact that the iodine-iodine bond is much longer than the greater size of iodine. That's nuclear repulsion. Here we get some nuclear repulsion that results in this bond angle strain and causes the sigma bond here, the sigma bond, it isn't really a sigma bond because the electron density isn't between the nuclei, it's being highlighted. And in fact, causes the bond dissociation energy to be almost identical at about 65 kilocalories per mole to the bond dissociation energy for a pi bond. So these aren't truly sigma bonds because the interorbital angle and the bond angle is constrained by the equilateral triangle are so far apart. They are less different for cyclobutane because 90 degrees is closer to 109.5 degrees than it is 60 degrees. And by the time you get to cyclopentane, the bond angle strain is minimal because the bond angle for a regular pentagon is very close to 109.5 degrees. For a regular hexagon, it would be 120, so you start getting bond angle strain in the other direction, where the orbital angle is not large enough to be the preferred angle for the regular polygon. But as we've seen, for the larger rings, the 6-membered rings, the 5-membered rings, the 7-membered rings, the molecule is no longer planar. So there's some deviation in the actual bond angle versus what it would be for a regular planar polygon. So what we see here is a difference between the bond angle and the orbital angle call it bond angle strain. The reason for it is because the electron density can't get between the nuclei where it really wants to be to affect the bonding, and we have pi-like bonds. So that answers the question, what's the origin of the large amount of strain energy in the 4 and the 3-membered rings, where the strain energy is much larger than predicted from the eclipsings. But it doesn't answer the question energy for the larger membered rings, particularly the 6-membered ring, where if it were planar, we would predict that it should have 12 hydrogen over hydrogen eclipsings, 6 on the top of the ring, 6 on the bottom, and a total strain energy of 12 kilograms per mole. If we look at models for the 3-membered and 4-membered rings, and you use your Molly-Mod model set, you'll find that I can't actually put regular bonds like I have with the carbon-hydrogen bonds in between all the carbons. If I tried to put a regular thick bond like that here, I wouldn't be able to do it. It would stick out and it would snap. So they include these kind of bent, flexible bonds, and you'll notice that it's pretty obvious when we look at this that the nuclei can see each other. There is no electron density right between the nuclei. The electron density bulges and it's out here on the side. And you can see that that's true to a lesser extent in the 4-membered cyclobutane as well, where the nuclei can actually see each other a little bit, and the bond is bulged a little bit. I wouldn't be able to get away with using the regular bonds to form those rings. But you can also see that there's not much flexibility, right? I can't really rotate around this bond without really torquing the other one. So it's pretty much constrained to be planar. Cyclobutane, however, is not constrained to be planar. It is possible to relieve some of that strain energy by twisting a little bit about the carbon-carbon bond, so we don't quite have eclipsing interactions anymore. So cyclobutane can take a configuration that twists. If you twist it too much, though, we introduce another type of strain across the ring, where these two hydrogens then get very close together. You'll see there's very little eclipsing now, right? It's almost a 60-degree dihedral angle, which leaves that eclipsing strain. But now I've got an additional strain here because these two hydrogens are being moved quite close to each other. So cyclobutane doesn't actually quite take a planar orientation. What cyclobutane really does is pucker a little bit, which you can show by drawing a system like this. And we have a hydrogen sticking up and a hydrogen sticking out. But now these two hydrogens are getting close enough to each other that if I torque too much more, they will actually overlap. This is called a transannular because it happens across the ring, and it's typical in even-numbered rings. Where you can actually have two hydrogens that are directly across the ring from each other when you pucker the system. We've relieved some of the eclipsing strain, but we've introduced a new strain. There's a limit to how much we can pucker it before this annular steric strain starts to become more significant than the acyclic-hydrochromal eclipsing strain than there would be otherwise. And it really hasn't done a whole lot to relieve bond angle strain when we do that puckering. We're still working with bond angles that are much closer to 90 degrees than we are to 1 and 9.5. So this transannular steric strain is seen in cyclobutane. It's also seen in cyclohexane, which we'll see in the next